Thank you for attending today's Thorlabs webinar. I'm Melissa Eberle, your moderator for today, and a regional sales manager at Thorlabs Imaging Systems Division, where we develop microscopy systems for the life sciences. Our talk today is on how to quantify, optimize, and select the best ultrafast laser source and optics for your multiphoton microscope. And I'm happy to introduce our speaker, Scott Domingue, who's currently the engineering manager for Thorlabs Laser Division in Boulder, Colorado. So his group's primary responsibility is designing and engineering laser systems to suit the specific needs of the life science community. Scott's previously worked at KM Labs, whose YB fiber laser products are now part of the Thorlabs products family. And during his time, he developed a 3-photon laser system, the Wi-Fi Optical Parametric Amplifier, or OPA. His work bridges the gap between the technologies developed in laser and biophotonics laboratories and the photonics needs of the life science community, with an emphasis on ultrafast imaging and spectroscopy. Scott has a PhD in electrical and computer engineering from Colorado State University, where he also worked as a postdoc developing a visible 2-color femtosecond laser system along with the transient absorption microscope. So one last thing before I hand it over to Scott. Please feel free to submit your questions throughout the presentation, and we'll try to get to them all at the end. All right, enough from me. Scott, are you ready to take over?
Yeah. Alrighty. Well, thank you, Melissa, for that introduction. Again, my name is Scott Domingue. I thought maybe one quick place to start, given that intro, is my actual group within Thorlabs. It's a little less well known, perhaps, than some of the other larger groups. The laser division is actually where we conceive, design, and produce the femtosecond lasers and products that you find on the website. It's a really exciting group to be in, and I'm happy to represent them today. So this talk is broken up into 3 sections. The first section is Ultrafast Basics, where we'll talk about kind of why we need such exotic pulses and really the physical background and basis for these pulses. The middle section, we're going to use a case study of in vivo deep brain imaging to really see how the parameters of the laser system and the microscope go together to really set the parameter space of imaging depth, frame rate, and things like that. Lastly, we'll kind of talk about how things maybe go sideways, where, in theory, things work really well, but then when you put them in the lab, maybe they don't work quite as well, and how we can measure that and maybe optimize on them. I've also thrown up some keywords to keep a watch out for as we'll be using them kind of throughout the talk. So to start with, Ultrafast Basics. Why do we need these pulses? So the goals here are to really set up kind of requirements from multiphoton excitation of why we need such exotic pulses. I mean, they're 10,000th of a billionth of a second duration. Why is that a requirement? And then at the end of it, we'll kind of pull up some spec sheets and kind of maybe do some basic interpretation. Okay, so to start with, we have single photon excitation, kind of confocal microscopy. What's going on? We're bringing light in. It's typically blue, maybe even into the UV, and we're going to resonantly excite fluorophores. And a key piece of this, as I've kind of shown pictorially, is we're going to get excitation through that whole focal volume, right? This is why we need a pinhole to do confocal microscopy to set up optical sectioning. By contrast, 2-photon excitation brings in 2 photons that will simultaneously be absorbed. And the major thing that does is it suppresses all of that background fluorescence. So we only have excitation in that one, in the focal plane. All right, and to do that, we really need ultrafast pulses. To really tease out why, let's talk about the sorts of power requirements needed to drive that simultaneous absorption event. So for 2-photon, the units are kind of weird. They're the Goeppert-Mayer units, named after the woman who conceived of this particular phenomena. And it's a weird unit. It's 10 to the minus 50. It's a huge unit. And ultimately, if we grind through the math, it means that we need powers on the order of 10 kilowatts to likely drive that transition, right? That's a welding laser, right? So we're not bringing welding lasers in to shine into a mouse brain, right? But it's an extremely high amount of power. For 3-photon, it's even a step further. That additional 3rd photon that's simultaneously absorbed and decreases the likelihood, meaning we've got to increase the power. And so now we're at weapons grade lasers, right? So how do we get around that? And that's where ultrafast pulses come in, right? This 10 kilowatts really is a statement that we need an awful lot of photons simultaneously present. And in the case of an ultrafast pulse, we're going to do this balancing act. We're going to bring in a massive number of photons, but only for a brief period of time. And so the duty cycle effectively is really low, meaning that our average power, and so things that we'll talk more about, the average power is really low. So we're not going to melt away the mouse brain, yet we have the power to drive this sort of nonlinear process. So hopefully that establishes the requirement or the need for these ultrafast pulses. And now what we're going to do is talk about how do we go about synthesizing them, right? And the starting point for that is to talk about CW light, or continuous wave light. So that's kind of this flat bar of intensity I have in the top left. And on the right is a cartoon of what this light is, right? If you recall from your high school physics, maybe, surely from your kind of entry-level physics in college, light is an electromagnetic wave. So it's a sinusoidal electromagnetic field, right? So that's what I'm showing on the right underneath the time part. And for CW light, it has this corresponding component in the wavelength domain where it's this really narrow slice of color, right? And that slice of color gives rise to the particular periodicity of that wave. And one of the beauties of CW light is we can really well characterize it with some basic measurements. So power is going to be one of the key things that we talk about, as it's what drives this nonlinear process. All right? So the equation of power is quite simple. It's energy per unit time. And if you haven't used these units in a while, energy is the work, for example, required to boil water, right? To take it from room temperature up to 100 C. So that's the work or the energy. Power is the rate at which we can do that work. So how quickly do we boil that water? And so when you take a laser diode and you shine it into a power meter, that's what you're measuring, is this kind of average power. Okay. By contrast, now let's start talking about how we get to an ultrafast pulse. And the starting point is actually a set of CW fields. So I have here 4 different CW kind of beams, as it were, each at a different color, different slice of the color spectrum. That different color gives rise to different frequencies of oscillation. So I have these 4 sinusoids here, and I've done something rather specific. I've given them a common relationship. So in some sense, that dashed line I threw in, that's time 0, and they all share it. So in kind of ultrafast parlance, that means they're in phase. And one of the natures of electric fields is that they can be added and subtracted, and it depends on that phase relationship. So in this case, they all have that central peak that are in phase, and so that would constructively interfere with build. Off-band of that, so elsewhere in time, because they have different periods of oscillation or frequencies, it's all gibberish, right? And in fact, that gibberish really looks like destructive interference. It would subtractively cancel out. And so if I take these beams and I superpose them in space, they would actually add. And if I had enough of these colors, they would actually create an intensity envelope in time, so that's that strong red curve, underlying which is an oscillating electric field. And that field, that oscillation pattern is actually damped down at the wings due to that destructive interference. We can take this a step further towards kind of really what we have out of a laser system, where we'll add some shape to that color content. We don't have kind of an infinite flat spectrum, but rather some sort of profile. And the profile of that color content actually physically will dictate the shape of the intensity profile. They turn out to be linked quantities. And not only they're linked very specifically. The more color content I have, the shorter a pulse in time I can create. And on the other side of that scale, the narrower slice of color I have, the longer the pulse is in time. And in fact, CW is an edge case. That continuous wave is an edge case, where if I have an infinitesimal slice of color, it will then specify a pseudo-infinite pulse in time, CW light, okay? So that's the physical underpinnings, but now we can maybe talk a little bit about, okay, we're using lasers to make them. They're not abstractions in a PowerPoint presentation. So there's 2 ways that we can really make these sorts of pulses. The first one is, well, they're more than this, but the 2 primary ones are laser materials. This is the first one, all right? And so I've thrown a couple up here, along with their associated kind of wavelength range. One of the really initial and kind of classic laser systems is titanium doped sapphire. It's actually pretty similar to ruby. Ruby is chromium doped sapphire, to give you an example. That color range, which spans something like 700 out to 1,000 nanometers in color, means we can either make pulses with really broad bandwidths and therefore really short pulses in time, or narrower bandwidths or color content that are tunable with somewhat more modest pulse durations. Similarly, we have ytterbium-doped fiber, which occupy a narrower range. We have erbium-doped fiber, which are out in the telecom band, out at 1,500 nanometers. And then there are things like, kind of exotic laser crystals, as I might classify them, like chromium 4-stripe, which you might not have heard of. And in reality, there's an entire smorgasbord of various crystals, but they kind of, in general, might all span within this range of colors. The second one are nonlinear sources, where we start with an ultrafast laser and we route that into a nonlinear system. And it has these key, some of the features it has, it'll give rise to these remarkable bandwidths or colors that you can push out of them. So, the OPOs, which have become a very typical laser system for two-photon microscopy, can do one of two things. They can be, again, kind of modest in color content, 100 femtosecond pulses that are super broadly tunable. And then folks like out in the high energy physics community would actually make super broad color content pulses that support, like these 5 femtosecond pulses to do really extreme light matter interactions. A key thing here is when we talk about duration is actually being somewhat specific. There's a lot of ways to define it. The definition that I use the most myself is just this full width at half maximum, and it's merely the width of the pulse at that half maximum point. It's really as the definition says. But you might also encounter someone defining it elsewise, such as the 14% kind of width or the 20 dB width. There's a lot of ways to do it, which will kind of move the numbers around. And really the only thing that's, to my mind, the most important thing is to just be consistent. If you're trying to compare two lasers, if their spec sheets are not using the same metric to define the duration, it's really, you then kind of don't know how to compare them. And the second part of that is duration is all well and good, but if the pulse is not clean in time, what does it really mean? So really having a sense for not only what that duration is, but what level of quality pulse you're going to deliver, right? That central pulse of the really scrappy looking pulse I've just added, it may share the same duration metric, but obviously it's a worse pulse. So the last major kind of component to these laser systems I'd like to talk about is that, we don't have one single pulse coming out of the laser, at least not with the lasers that we're going to talk about today. It's a train of them, many, many pulses per second. And what gives rise to that spacing of pulses in time? So for a fiber oscillator, we'll have like a ring. And for a free space oscillator, maybe we just have fundamentally, it's kind of two mirrors. And a laser inside of that is going to ricochet back and forth. And there's a component called an output coupler. And that output coupler can really be understood as a leaky mirror, where maybe it's 95% reflective as opposed to 99.9. And that 5% leakage is actually the laser that we're going to use. So if we kind of track a laser running around the cavity or a pulse running around the cavity, when it gets back to the output coupler, a little bit of light comes out, right? The pulse runs around the cavity again, and another pulse comes out sometime later. And that delay between pulses hitting that output coupler, really the round trip time of the cavity, that's what sets the repetition rate, or the pulse-to-pulse spacing of what comes out. It's also why, a laser manufacturer might be reticent to change the repetition rate of a standard product. It's really quite difficult then to go through and change the physical layout of their system. Okay, so we've kind of established the need for the pulses, how we kind of start to go about synthesizing them. Now let's dig in a little bit and talk about the power contained in these pulse trains. So again, power is energy over time, and the challenge here is what energy and what characteristic length of time are we even going to use? And so we'll start with the simpler of the two, the average power. The average power is really the energy contained in all the pulses within a second. All right, so it's, in this sense, I've shown this little pulse train to the right. It's the area under kind of the total curves over an entire second. And if we put some characteristic numbers to it, or some typical numbers perhaps, of 1 nanojoule per pulse, a pulse spacing of about 10 nanoseconds. So that would be a 100 megahertz laser, which is a little high for a 2-photon laser, but really in the ballpark. That comes out to be about 100 milliwatts, right? So pretty modest average power. Right. This is what happens if you take, say, a Tiberius laser and just fire it into a power meter. What you're measuring is this average power. But the thing that does the work for a nonlinear process, like 2-photon excitation, is the peak power. And the peak power is really when we zoom in and look at the characteristics of just one pulse. So now the energy is the energy contained in a singular pulse. And we're kind of making the assumption that all the pulses in the pulse train are exact copies. And that's usually, it should be a pretty good assumption. The time component is the duration of that pulse, of that characteristic pulse. And here I'm just going to use the full width half max. Things will move the number around depending on how fancy you want to be with this metric, but if you kind of just keep it consistent, you'll always be able to compare, in a sense, pulse to pulse, at least in terms of relative better or worse. All right. To put some typical numbers to that, again, a nanojoule per pulse, we're going to give it 100 femtoseconds, and that peak power is going to work out to be 10 kilowatts, right? So I've set this up on purpose. That's what would likely drive, and by likely I mean, you're going to get a 2-photon excitation transition per pulse. At an average power, 100 milliwatts, that would be sustainable within an in vivo mouse brain setting, for example, right? But to characterize what does that pulse profile look like, you can't just use a power meter. You can't even really, a photodiode, even though you're going to see a little blip or a pulse on your oscilloscope, it's not actually the peak power. You're really seeing an average representation of that. To measure the pulse, you really need an optical nonlinear event. So we have techniques that do this, such as frequency resolved optical gating, or FROG. That really will characterize, in some sense, the entirety of the pulse. You'll know an awful lot about it. Autocorrelation, will give you the pulse width, and maybe combined with some other things like the spectrum, you can learn some things. And then after, but there's spider, there's grenouille, there's tadpole, there's sea crab, there's a whole menagerie of animal acronyms that you can use that are required if you want to know the actual pulse profile. So let's talk about an actual laser. Before I dig in too far, I actually want to try and clear up an ambiguity that was brought to my attention when I was preparing for this talk. I'm going to say the word pump laser or pump a lot, and I mean something specific. And if you're looking to buy a laser, you're going to hear maybe that same term in a different context. So for a Ti-Sapphire laser, we're actually going to pump the Ti-Sapphire crystal with a green laser. It's a 1 micron laser that's frequency doubled to green, and it pumps the Ti-Saph laser. So if you're buying a laser, you might hear that, and that's maybe what they're talking about. What I'm referring to is using the output of that Ti-Sapphire laser to pump the 2-photon microscope. It's just maybe to clear up a potential ambiguous term. Okay, so let's look at that spec table. So we have the pulse width, we're seeing 140 femtoseconds. For the average power, we're seeing that it's dependent on the color, and so I've included a tuning curve that underlays across that average power as a function of wavelength, some fairly typical 2-photon absorption spectra. We also see the repetition rate, 77 megahertz. So a few watts, 77 megahertz, we can actually go and turn the crank, do a calculation of how much pulse energy is there per pulse. So at its peak, this is a 30 nanojoule laser system. We can contrast this with a 3-photon laser, where we're going to move out from the kind of near infrared around 900 nanometers out to 1300 nanometers. So there's a lot of components to this, but the column that says signal is really the 3-photon laser that you would use to go and excite GFP, for example. So that's what's shown with the blue dots in that tuning curve. You'll notice the average power is actually pretty comparable to our 2-photon system, but the repetition rate has come way down, right? And so if we have a much lower repetition rate, we have to have a lot more pulse energy to drive that same average power. So indeed, instead of 30 nanojoules at its peak, this is a 400 nanojoule at its peak laser system. And in this case, it's also tunable both in color and in repetition rate. A novelty of this laser is that it emits the same kind of pulse energy independent of repetition rate. So that curve to the right, it's roughly 500 nanojoules across that rep rate band. And so as the repetition rate increases, I have more pulses, therefore my average power is growing at a fairly linear rate, right? So if you're looking at one of these lasers, there's kind of a lot of components to it. You need to really know who's scaling with what. Okay, now we have a laser. Let's go start talking about how all of those parameters start to couple to a microscope and the two-photon process. And to do that, we're going to use an example system. We're going to use deep brain in vivo imaging. And the reason for that is because it so nicely couples all these parameters together. If you have a much thinner sample or a more optically dense sample like organ tissue, all of the premises are going to stay the same, and really it's just you're going to move, the curves are going to scrunch up on one side of the graph. But in vivo brain turns out to be a really nice case study to understand how these things couple together, right? So here's our goal. We're going to try and image as deep as we can, right? And the main thing that we're going to have to combat are these three constraints that limit us. The first is sample damage. Not only do we put a bunch of time into a mouse, given this example, and we don't want to just destroy it. We need to be good stewards of that mouse. So we don't want to damage. There's going to be some sort of power limit to this process. The second is, as we push light down into biological media, it attenuates. So we lose photons as we move down to that focal volume. And that's something that we're going to have to combat. Third, while it's unlikely that we have out of focus multiphoton excitation, it's not forbidden. And in fact, at an extreme case of depth, it's what limits us, okay? Now we're going to dig into each of these individually. So the first one is the damage mechanism. So these are femtosecond laser systems. If you get a mirror from Thorlabs, it will have engraved on the perimeter part number. And that's done with a laser system. Right? We could similarly ablate mouse brain under the right conditions. But typically, that's not the damage mechanism. It's not that it can't be, but it almost, in all two-photon cases, is unlikely to be that way. And in fact, what it is that we bring light into the brain through this focus, and then below that focus, it kind of diffuses. And researchers have found that it, in fact, is this broad area, a few hundred microns below the surface, where if we continue to increase the amount of power we're bringing in while scanning, at some point the vasculature cannot continue to remove the heat, leading to a temperature rise in the brain in that area and ultimately damage. Based on immunohistochemistry experiments where they're looking for heat shock protein, and it being present and not present depending on the amount of power used, they've been able to really pin down thresholds of average power for some of these really key cases. So for 922 photon, that's 250 milliwatts. Then below that, it seems to be the case that we don't damage. For 3 photon, below 150, same thing. Now that's not to say that there aren't other effects like phototoxicity and things like that. But 1300 nanometer light relative to even 800 nanometer light is orders of magnitude less phototoxic. So it's not that there can't be other mechanisms, but for some of these really big applications today, this is believed to be the predominant damage mechanism. What's really nice about having a number like this is we can really kind of set up a budget and do accounting of our laser system, right? We know for the case of 2-photon, we want at least 250 milliwatts coming out of the objective. Okay, that means I can go backwards and tally all of the things up in my microscope system. The objective, the losses intrinsic to the microscope itself, delivery optics, the beam blanking system, the dispersion precompensation, all of them up, and basically do some simple arithmetic to figure out how much power I need coming out of the laser to fill my budget. So that's the language I'll be using. I want to be able to fill my budget means I can deliver that sample maximum, 250 milliwatts. Okay, and in this case, it's pretty modest. It's less than 700 milliwatts, right? And we can think about how does that scale. So I'm going to go back to that Tiberius tuning curve, right? I want to have more than that 700 milliwatts everywhere. And so for most of that range, I do. Out into RFP, my tuning curve starts to diminish, and so I'm below kind of that optimum power out of the laser to fill the budget. And so two things could happen, right? One is that we could have a more sensitive sample. That more sensitive sample maybe can't take 250 milliwatts, maybe it can take 50 or less. That's going to pull that budget line down, meaning more of that tuning curve would really fill it. By contrast, maybe we have a lossier system. And I used the 2-photon objective from Thorlabs. It's extremely transmissive. So maybe instead of 80%, our objective is 50%. So that's going to move up the power requirement on the laser to, again, fill the budget to have the maximum amount of power supported by the sample coming out of the objective. Constraint 2, scattering and absorption. So light, as it passes through a medium like glass, it's fairly transparent. Unlike glass, our bodies, our tissues, have a lot of particles that are on the order and larger than the wavelength of light, okay? And so for brain, this is a pretty well understood kind of set of systems. There's two major components that really govern how we lose light. And the first one is that interaction between particles, or molecules, cells, red blood cells, the intracellular vesicles, kind of all of it, will scatter light. So it's called me scattering. And it's why the sky is blue, right? White light from the sun comes through our atmosphere, scatters off those particles down to us. We look up, we see blue. And by contrast, sunsets are red because all the blue has been scattered out of them. Same happens in the mouse brain, right? So the shorter wavelength you are, the more scattering we get. The longer wavelength we are, the less scattering. The second one is water absorption, which you see kicking in as this black curve around 1450 nanometers. So that's the peak of an absorption curve, but it's the case that curve really extends all the way out into the near infrared. So there's less water absorption at 800 than say 1300. And the combination of those two things, me scattering and water absorption, combine to really attenuate these photons. So what do these numbers mean? So if the combined attenuation length for 900 nanometers is 175 micron, what that physically equates to is the power down 175 microns below the surface is 37% of what it was at the surface. All right, as we go to longer wavelength, that length increases. That means that now it doesn't happen that we're 37% of the power at the surface till, say, 250 micron deep for 1100 nanometers. We can populate in some typical kind of 2-photon absorption spectra to really see how these start to map out. We see the really distinct kind of second biological imaging window out at 1300 nanometers and 1700 that straddle that water absorption line. But a key thing here is that we notice, right, the 1300 nanometers to do 3-photon GFP is much closer to that water absorption. It's farther out. And in fact, more light is absorbed at 1300 by water, and that's what gives rise to this reduction in the power threshold at 3-photon versus 2-photon. All right. So we now need to combat this, but the question is, how much power do we actually need at any given depth below the surface? And maybe counterintuitively, if you think about a fluorophore, I'm going to bring a pulse past it. What's the maximum fluorescent light it can generate? And it turns out it's one. It's one fluorescent photon. It's the maximum you can generate from one fluorophore per photon or per pulse, excitation pulse, right? That means there's some optimum pulse energy that will get to that balance, one transition per pulse per fluorophore. Energy in excess of that does no additional imaging work. It doesn't generate more photons because it can't. The fluorophores have already done the transition. Okay. We can actually calculate what that saturation energy is, what it's called, but that optimum pulse energy, what it is. And that way we can shoot to have that and only that down at some depth, even after attenuation. So for some given kind of focusing conditions, for a given typical GCamp fluorophore cross-section and a laser term of say 100 femtoseconds, we get a saturation energy of a little less than half a nanojoule. Okay, so now the goal will be, let's maintain that 0.4 nanojoules even as we lose power as a function of depth. So we'll have to start with more so that we still have 0.4 nanojoules for every depth. All right, so that's what you're going to see here. So at z equals 0, we want 0.4. But as we go down at the surface, we're going to need more and more pulse energy to continue to maintain that 0.4 nanojoules. What this curve hasn't shown yet, however, is that we have that average power limit. And so if we think about how that average power changes as we crank up the pulse energy, so as we tune our attenuator as we're imaging deeper and deeper and deeper, at some point we're going to limit out. We're going to hit that 250 milliwatt threshold, right? So up till 330 micron, we're delivering optimum pulse energies at depth. Beyond that, we're average power limited, which means we're going to start losing two-photon signal because we can't deliver enough pulse energy down deep because we're average power limited, right? How do we move the curve, as it were? How do we move that kink point where we're average power limited deeper? So one thing we can do is we can change the color. If a redder color attenuates slower as a function of depth, then we need less energy at the surface to achieve that optimum pulse energy down deep, right? So changing out in color, I know means changing fluorophores. I know that's not true. But this is really to try and create the landscape of how these things move around. So between 940 and 1100 nanometers, we have a full 100 micron benefit, nothing more than just changing the colors. That's assuming everything else stayed the same. Another knob we might employ is the repetition rate. And I'm merely playing the trick. I need the same pulse energy at the surface. It's going to attenuate down to hit the optimum. I'm just going to bring in fewer pulses. And so the average power will come down. That will shift this curve out deeper still. The combo of those two starts to be pretty strong, right? From 100 megahertz to 25, blue to red, we gain almost half a millimeter in depth. So it's a fairly strong lever arm. Let's look at the third constraint. It's this background generated fluorescence. So as I said at the beginning, it's unlikely, but it's not a forbidden process. It's just that we need a lot of intensity, a lot of photons simultaneously present in space and time, both, to generate it. And so let's talk about the two things that are trading off as we try to image deeper. The first one is reducing the intensity. It's suppressing the capacity to do two photon. And that's that the area on the spot at the top surface is growing larger. And it's growing larger quadratically with depth. And that's diminishing the intensity, power over area. So it's suppressing the two photon effect. But we're trying to go deeper. So we're taking our attenuator and we're exponentially ramping up the energy and power as a function of depth. So we have these two things competing. And it turns out to be the case that exponential growth eventually dwarfs that quadratic decay. And on a limit, when we try to image really deep, we will have as much fluorescent light generated at the top as we do in focus. And we have no confocal pinhole, so we can't discriminate between photons and where they're generated. And so we get this washing out of our image. And we can actually take this a step further and really zoom in on the two means by which we lose image sensitivity. The first is when we don't have enough pulse energy, right? So let's imagine we're imaging a sample and it's got this nice repeated structure all the way down. And at the top, we get these really strong lineouts, right? So that's this yellow curve. Hopefully you can see that. As we go down in depth, that lineout, the peak of that nice strong feature washes out. It comes down to this dark background, right? So we go to this black background, right? That's this case where we just don't have enough pulse energy down deep to optimally drive two photon excitation. So we fire a pulse in, but we just don't have any excitation happening down at our focus. Now let's say we have all the power we want. We've dropped the rep rate, we've got tons of pulse energy. Now as we go down deep, that line out stays nice and proud. But the background starts to come up, so that's that blue curve. And in the limit that we go extremely deep, what we actually have is enough fluorescent out of focus light that we don't have a dark background anymore, we actually have a white background. We go to this, a snowfield or a blizzard effect. This is a fundamental limit. That signal to background ratio is a fundamental limit that caps both two photon and three photon in terms of how deep you can go. There's not this thing that without a pinhole, you just can't keep going deeper. It's also nice that it's a calculable thing. So for two photon, you can go to between 5 and 6 times the attenuation length. So those were those attenuation lengths that were the combination of me scattering and water. So for 1100 nanometers, fundamentally you can get resolution up to about 1.2 millimeters, extremely deep, right? And the reason that you don't see a lot of that is if you also look, the next part of this is you'd have to go to repetition rates where there's really not a commercial two photon laser system that's just ready and waiting for you, okay? We can now put all these three things together. The average power limit, the need to combat scattering and losses as we propagate down to the focus, and this fundamental background. So if we start building this curve out, we've got kind of the optimal pulse energy is we're running our attenuator up to the point that we hit our average power limit, and that's where we hit this suboptimal pulse energy at depth. We can add in these kind of fundamental limits in terms of the signal to background ratio. These are pretty far out there for kind of the very typical 2-photon wavelengths, which is to say that really it's because we're usually suboptimally pushing pulses way down deep that we have these kind of limits in terms of whether or not we're seeing features down to 300 micron versus 800, depending on the labs we're in. We can add to this 3-photon, which really starts to bring in why it's such an interesting modality. So the first thing I'd like to comment on is that, the starting point was 10 megahertz, already much down from 100. And you'll notice, because we need so much pulse energy to drive that process, we hit our average power limit very quickly. In fact, we hit it, at like 100 and something micron. That's why, at shallow depths, 2-photon is the superior imaging modality. We need a lot less energy to drive the process. As we come down from 10 to 1 megahertz, we can deliver optimal pulse energies, though, really quite deep, out to almost 900 micron, before we hit that 150 milliwatt limit. That is why you see so many nice papers where they're seeing features, neurons coming down to 1.3 millimeter, because at a megahertz, that's about the limit. Below that, you're going to start going into that dark limited background where you're just not able to get the pulse energy there. The folks doing stuff where they're imaging really, really deep, they're actually coming down further in repetition rate, something like 200 kilohertz, so a fifth of a megahertz, right? It's there. Fewer pulses, we can get deeper still. The fundamental signal to background ratio for 3-photon, because it's a higher order process, is suppressed even harder, is now out to like something like 3 millimeters. Right? And again, the reason that you don't see tons of 3 millimeter work is because you'd be at these really comically slow repetition rates. And the thing that repetition rate really does in this case is it maps to frame rate. 1 megahertz is 1 million pulses per second. And that's a large number until you think about how big our pictures are, right? If I want a megapixel image, it's 1 million pixels. I would need at least 1 pulse per pixel to make an image. So at 1 megahertz, I cannot generate a megapixel image faster than once a second. And worse, at 200 kilohertz or a fifth, now I'm an image every 5 seconds, which may be fine if you're trying to do structural imaging, maybe not if you're trying to do dynamics. So by contrast, 100 megahertz and 25, those are up in the tens of frames per second. So back up into the video rate sorts of imaging acquisition speeds. Okay. So we're now into the third section. So we've had our crash course. We've tried to tease out how a lot of the parameters then map into an in vivo setting. So now what we're going to talk about is how things aren't always as perfect as they are in reality. And I really like this quote, and I feel like ultrafast lasers and optics really are, they prove this to be true. In theory, there is no difference between theory and practice, but in practice there is. So let's talk about how some of this deviates. Up till now, we've really assumed idealized systems. And so now I want to talk about 3 things in which they can become non-ideal. The first is how the pulse we're shoving in, how it can change the signal level. Then we'll talk about letting the system become suboptimal. And then we'll talk about how to tune it. Okay, so we'll start with a perfect system still and focus on the pulse we're bringing in, how it changes the sort of fluorescent signal we're getting. So what this expression shows is the fluorescent power of the multiphoton process, so the fluorescent photons we're capturing, how it depends on the input pulse in terms of average power, P, the repetition rate, F, and the duration, tau. N is the nonlinear process, so 2 for 2-photon, 3 for 3-photon. And the first thing we're going to do is look at power limitations, because they're the largest lever arm that we have on the system, the strongest scaling factor. So there's 2 ways that we might be power limited. The first is when we don't have enough laser power coming out of the laser to fill the budget. And so we're never delivering optimal pulse energies at any depth. So that's that A section of the curve. We're not even able to reach that dashed line. The second is after we have that, we can fill the power budget, but we're trying to go deep and we're average power limited. And therefore we're below the optimal excitation energy. So for 2-photon, we'll have a quadratic penalty in terms of the number of fluorescent photons we're generating. And for 3-photon, it's cubic. Again, that's the largest lever arm we have to improve our signal quality. Okay, let's say we can fill the budget and how these other parameters come to. So repetition rate and tau. Repetition rate, usually we don't have a strong means of acting on. Those fast beam blankers we use to shutter on flyback aren't fast enough to actually do changes to the repetition rate. So duration. So I've shown a 50 femtosecond pulse in this curve to the right and a 200 femtosecond pulse with the same energy, right? That much taller 50 femtosecond curve, that's why you would want to use it. For a lot less pulse energy, potentially, you can bring that curve down and still drive the process really strongly. So I've normalized the strength of the 2 and 3 photon signals to a 100 femtosecond pulse. So it's set to 1, and we're going to look at how things get better or worse. So for 2 photon, you could see a 5-fold improvement down at 25 femtoseconds. And by contrast, as you go out to 500, you're going to lose, 75% of your signal. For 3 photon, it scales a bit more aggressively. And so the picture actually at the top is a poorly compressed pulse where you're not actually delivering a short pulse to the focus, getting it optimized up with your microscope system. And now that brightness is purely based on the reduction in duration, right? And so you're just generating more fluorescent photons to capture. Okay. That's all well and good. Can we deliver a 25 femtosecond pulse to the focus of our objective? Punchline is not without great effort. Let's talk about why. If we look at a laser system or a microscope system, we have a laser, we usually have a dispersion pre-compensation element, and we have a microscope. Microscope is a ton of glass. When we push light with a collection of color through it, those colors propagate at different speeds. And so when they come out of, literally tens of centimeters of glass after the scan lenses and tube lenses and objective, the reds are out in front of the blues. They've moved through the system faster. They've smeared out. We would call this a phase. So, but it's this linear phase or smearing of the colors in time. And the microscope is going to do that. And the precompensation device's job is to try and exactly mirror and invert it. So to smear it out with the opposite sign, blues in front of the red. So when it goes through the microscope system and out of the objective, they're all back together in time and therefore short. And the key thing here is that, ours and everyone's precompensation devices are really hoping to try and do a linear compensation, which is to say that smearing effect is linear, right? And the reality is it's not. Over a small finite amount of color, it will look linear. And the more and more color we add to it, the less and less linear it will look. And that has a pretty strong impact. And it means that there are limits about the pulse duration we can push through these systems and then actually deliver it short to the specimen. So what I'm going to do is I'm going to take 3 case pulses, 25, 50, and 75 femtoseconds. These are idealized pulses where they're all equal in energy. So the 25 femtosecond one, you're thinking, that's the one I want to use. And I'm going to numerically propagate it through precompensation device and a model microscope. And this is what we get. Okay. I've left that ideal 25 femtosecond curve in, nice and tall and proud. Those percentages you see are the percent of the peak power that we're getting to relative to the ideal of each of those pulses. So the 75 femtosecond pulse, basically perfect. 50 femtosecond, it's better than the 75 because it's shorter, and it's also basically perfect. The 25, however, is dramatically worse than its ideal peak power. And in fact, it's not really any better than the 50 femtoseconds. So if you spent money to get there, right, that's wasted money. You would have been better delivering a 50 femtosecond pulse because you're going to get the same fluorescent signal. All right. Another place that this may crop up are the mirrors. So here I've got 2 mirrors. I've got an EO3 broadband dielectric mirror. And if you've got a multicolor set of diodes routing into a system, this would be a great mirror to go bang around those laser beams. Problem is, it's not an ultrafast mirror, although its breadth may trick you into thinking that it is. So I've shown an actual ultrafast mirror, and you'll notice some really particular characteristics to it. It's super flat, it's got a lot of ringing. And basically, it's where you sacrifice what's out of band to really have a flat curve inside. And you'll notice you'll often see this second graph that they'll include, this GDD graph. Really what that is it's telling you about that linear smear of color out into time. And for our purposes, we want that mirror to look like a bunch of zeros. If it's a bunch of zeros, then it means that curve is relatively well behaved. If it has a lot of deviation in it, then it means that there's a bunch of additional structure that our precompensator can't account for, right? And it turns out that the ripples in that EO3 look like uncompensatable phase. And so I'm going to do the same thing as I did previously. I'm going to take 4 model pulses, I'm going to bang them off 4 numerical versions of that EO3 mirror and see what happens to an ultrafast pulse. And so again, I've kept that perfect 25 femtosecond pulse, but you'll notice it's now the worst pulse of the bunch, right? So merely 4 mirrors reduce that pulse to being the worst pulse you could have sent into the system. And in fact, all of the pulses are basically no better than that 100 femtosecond pulse, which is still nearly ideal. All right. Now, again, the problem here is that you might think, oh, I have a precompensation device. I'll just clean that up. And the reality is it's a ill-behaved system. It's not just a few silica lens, and it's an uncompensatable corruption to the pulse. So there are several key takeaways here. One was that if you remember those previous curves, the wavelengths really matter. You need to know whether or not those mirrors were designed for the wavelengths you're trying to use, right? If you have a 920 nanometer pulse, it's going to have some color content. And the shorter the pulse, the broader that curve is going to be. Do your mirrors support that bandwidth? The other 2 main ones are these effects are cumulative, right? So they just keep adding up, which really starts to favor longer pulses, interestingly enough, because the shorter they are, the harder it is to deliver them. The second is, this is really the importance of things that are like these low dispersion optical systems, right? Usual flyback systems, or flyback shuttering and beam blanking and attenuation, usually we use a thick crystal. We've added a crystal to the system. It accumulates the total amount of phase that we've got to compensate for and how linear and nonlinear it is, right? So we, for example, in the laser division group, have developed a version of that fast shuttering device that's all reflective. We basically took all the glass out of it. It's really trying to eliminate those effects. That's the premium of ultrafast systems. If you've ever balked at the price, and that's unfortunately, it's that they require a lot of the optical performance so as not to degrade the pulse that you're trying to deliver. That's just 2 effects. You know, lenses, thankfully, aside from their glass material, don't do much more. But these are the kinds of considerations that, you know, one bad mirror in your system, if you're trying to be a really short pulse system, can really matter. Okay. We've built up a laser system and a microscope system. We have our precompensation device. How do we do some characterization and get it tuned up? And one thing I'm going to try and help with, and it's a trick that I learned in grad school, I think is not as well known, but how do we do diagnostics where we're not actually watching live updates of a 2-photon image, right? Where are we bleached? Are we in focus? There's a lot of unknowns. How do we get a better signal? And the starting point is I'm going to show some photodiodes. So I have here a gap photodiode and a silicon-based photodiode. So those are just the semiconductors in it. And if you look at the responsivity as a function of wavelength, and I add in the single photon GFP absorption spectrum, you'll notice it and gap align pretty well. Well, we know if I shine 900 nanometer ultra-fast light into GFP, I get a 2-photon excitation. And it turns out the same actually happens in a semiconductor. So we can get a nonlinear absorption. So if I fire 900 nanometer light into a gap detector, it's not sensitive to the average power, it's sensitive to the peak power. Similarly, if I fire into a silicon photodetector, 1300 nanometer light, I get a peak power sensitivity, not average power. And it's the peak power that's going to drive the process. And so I can build up basically a power meter that's seeing the thing I actually care about, right? As I move my dispersion precompensation device, my average power is not changing, but I'll get now a voltage out in a sense, you know, a power meter-like effect that's the height of the pulse, okay? Literally, you can take a stock photodiode, biased photodiode, put it in the focus of your objective and do that sort of analysis. Now, big warning, semiconductors have extremely strong responses. If you do this, and I encourage you to, keep the power low. You probably don't need to be in focus, so you should really come at it the first time very conservatively. Otherwise, you will just destroy that power meter, or that photodiode, rather. But if you put that photodiode in or near the focus, you appropriately terminate it, and I'll comment on that in a minute, you're literally going to get a voltage readout. Now, photodiodes are fast response devices. Now, they don't see the true intensity profile, but they're going to show you blips on an oscilloscope if you put it to an oscilloscope. Each of those little blips, as you change your dispersion precompensation, will get taller and smaller. That's your peak power feedback. If you want it to be something that's more DC, you'll need to think about how you're terminating it. And if that sounds weird, you can go ahead and you'll see my email address in a minute. Go ahead and ask, and we can work through that. In terms of like things like, okay, so we do it for a photodiode, then we put our sample in, there's a cover slip. That's maybe going to mean that you're going to need to do some small tuning, but it's the case that you really have found kind of the global peak. Lastly, this is a relative measurement. So if you feel like, man, I'm still orders of magnitude away from where I think I should be, you really have to go to something that's more sophisticated. You really need to know, are you delivering a short pulse? And there's no way to know that really without doing the measurement. This is more involved, I'm sorry to say. You could collimate your output and put it into an autocorrelator. Really, one way to do it would probably be to do an elimination study. Pull your objective out, check it at the entrance to your microscope. All the while, though, you need a device like the Thor FSPC to really do, no, that's not our, wrong part number, excuse me. You need an autocorrelator or a frog or some device like that to actually do some characterization of the pulse itself. That's hard, but really this is the case that there's kind of no substitute for knowing what your pulse is. Again, if you have a really short system, you're trying to do 3 photon, someone put the wrong mirror because it was put in the wrong box, you could have one mirror in your setup between your laser and your microscope, corrupting the whole thing. That's actually the end of our talk. So a bit of a whirlwind. To kind of recap, we talked about some ultrafast basics, why we need these pulses and how we synthesize them and what they look like on a spec table. Hopefully that particular case of kind of deep in vivo imaging helped kind of set up a picture of how some of these parameters are coupled together in terms of average power, rep rate, and pulse energy. And then lastly, these kind of, I know those were quick case studies, but the goal of that was to really impress that the details here really matter. So with that, I want to thank everyone who has tuned in. I want to thank the media team for helping me get to do this, and the laser division for letting me take some time to actually put this together. With that, I'd like to ask the moderator if there are any questions to go ahead and toss them out.
All right. Thanks, Scott. That was a great talk. Thank you very much. So I'll kind of go through the questions. We do have a couple questions, and I'll publish them as I go so that everyone can kind of follow along. The first question that came in is, what's the pulse duration for the Wi-Fi and OPA system?
Great question. So the Wi-Fi OPA is kind of a 2-part laser system. It's one of these things where we start with an amplified 1 micron ultrafast laser, so that's a laser. The pulse duration of that 1030 pulse is around 150 to 175 femtoseconds in duration. And by contrast to the output of the OPA, it's a microjoule class laser, so it's a few microjoules of pulse energy. The output of the OPA has a varied pulse duration as a function of wavelength. At 1300 nanometers, it follows the 1 micron, so it's about 150 femtoseconds also. And then out at 1700 nanometers, for reasons, it's shorter, so it's about 50 femtoseconds.
All right. All right, so the next one is, can a 2-piece system be adapted to a 3-piece system? And if so, they ask what would be a simple task to do, but maybe you can just kind of go through what are kind of the key elements for converting 2P to 3P and what they would need, and to really like understand to be able to kind of do that conversion.
So there are 2 key differences between a fairly typical 2P system and a 3P. So the 2P system is going to have a 2-photon laser. Hopefully it's clear now based on rep rate and pulse energy. It's not appropriate for 3P. And the second one is in the internals of the microscope, the actual things doing the laser scanning. So if you have a video rate capable 2-photon microscope, those scanners are moving too fast to do pulse per pixel down at the lower repetition rates of a 3-photon system. So you would need to kind of figure out, you may have a resonant galvo system or scanner in your microscope, and you would really need a galvo-galvo scanner is what it's called. And it just means that the scanning of your pulse and the output of your objective is slower. And then the next, so the scanner is one part, and then the next major part is a 3-photon pump laser. So something like the Wi-Fi OPA. There are others, I won't name them, but something that has the pulse energy and rep rates required for that process. The last little bit are the filter optics need to transmit the longer wavelength pump light. Similarly, the objective, out of 1300 nanometers, not all objectives are going to be very transmissive. In fact, they may not be designed, if they're not designed for it at all, if they're really a confocal microscope or objective, they may be very poor in operation at 1300. So maybe there's three. The optical components, which are really, I think the Cerna system, for example, you really could just get new dichroic mirrors to do the epi filtering. That's pretty easy. And then the bigger parts are the scanner and laser.
All right, great. To go along with that, you kind of started mentioning about the 3P laser. So the next one is, are there recent advancements in 3P type lasers that really enable 3P? What are some of the challenges in getting better / less expensive 3P lasers?
That's a great question. While we were at KM and now continued at Thorlabs, there's a heavy effort involved within the kind of total ultra-fast laser commercial community to make these lasers. So there's new ones on the market from kind of all of the major companies, us now included, that have gotten better. One of the major things that was harder about these lasers is that you start with a high power ultra-fast laser. So the challenge to that is I'm now going to take upwards of 10, 20 watts of ultra-fast light, and I'm going to route it into a nonlinear system to convert into these new colors. And it's just the case that that's a lot of average power. A mirror mount that sees a surface reflection from a lens, you can now heat to the point that your beams move around. So some of the early teething that you saw in the biophysics labs like Chris Hsu in those early 3-photon lasers, either their home build or even the early commercial versions, is that they're hard systems. And that's part of why they're so expensive, right? You're having to really buy not one laser, but kind of two. You're buying an ultra-fast laser, which are also very high power. Both of those things combine to make them not particularly inexpensive. And then you're routing that into now what's kind of quote unquote this nonlinear laser. So it's this compounding of things. And while there's, we're sensitive to the high pressure to come down in cost, it's also one of those cases that, when you need a race car, you need a race car, and they're not cheap to build.
All right, we have one. Can you talk a little bit more about how a laser changes wavelength efficiently? Is it mainly tuning a prism?
Yeah, it depends on how you're doing it. So in a TISAF oscillator, the TISAF crystal naturally can support these extremely broad colors or a wide tuning range. And then the way you go about affecting that tuning range, I think, is varied. So, you can move a prism around. That starts to be how fast can you move a prism? It doesn't sound like much, but now small masses, being able to move them accurately and precisely and very rapidly becomes a challenge. How quickly you can do that, that's the type of areas we're extremely proud of how well we have solved that problem. For something like an OPO, which is now you're taking laser going into a nonlinear system, you have a nonlinear crystal that's giving rise to the new colors. You're having to change angle on that. You're having to change, those systems actually start to look a little bit like an interferometer. And so you're also changing relative delays of when things arrive. And so how quickly you can kind of do all of those tasks will map to both how quickly you can do the tuning, and because it's a nonlinear system, that new tuning curve of the OPO is really set by, the process of combining multiple ultra-fast pulses within a crystal and what that crystal can support.
All right, great. This one's more on the pulse duration. So what effects do the dichroic optics typically have on the pulse duration?
Sure, great question. So it's the case that for something like a really simple AR-coated lens or an AR-coated window, that little bit of ripple on the order of, 0.5% or something for an AR coating doesn't strongly impact duration. For a dichro, that will remain true, but where it breaks down is whenever the color of the, so we're going to bring 1300 nanometer light through the dichroic optic. And we probably reflect, let's just say we're going to go through it. So where it's different than an AR coating is when the pass band edge, which is steep, starts to come onto the color content of our pulse. So if you start to see a little bit of clipping, so if you took a power spectrum, so if you measured the color content, before and after that dichro, and you see a little bit of clipping, that would be an indicator that you're actually going to start to also see a contamination of your pulse in time. You'll see some corruption in it, and you'll have a worse pulse. So lower duration and also a shedding of energy out into kind of some trash in time.
All right. So we have one that's a little more of a, application based. So I think I'm going to publish it first so people can kind of read along since it's a little more in depth. For in vivo imaging dwell time, per location in the tissue is crucial since the subject can move and the tissue can pulsate. The general accepted speed is 15 to 30 hertz, so frame rate. This also allows for more safe exposure power since you have to move the laser faster to scan the tissue area. What process or approach would you recommend to improve SNR in this scenario? So it's the kind of frame rate versus SNR with your 2-photon laser.
Yeah, so you have one thing going for you whenever you have high rep rates. So if I recall having made the curves for, the number of pulses incident on a particular pixel location, even up to say 15 hertz, at kind of these kind of typical 80, 90 megahertz laser systems, you actually have multiple pulses incident per pixel. So you're already getting an increase in SNR that's just through the summation of additional pulses. So that'll just scale with N. I think really the way people are getting around this, as you notice, some of these curves are pretty much locked. If your rep rate is locked and the average power coming out is locked, so one version would be if you're doing unidirectional scanning, you'd want a beam blank so that your duty cycle effectively goes down so that your average power when on could, in a sense, go up so you could deliver a little bit more pulse energy, assuming we're deep enough that we're not already at that kind of optimum limit. The second part of that, though, is, and this is really what people are more trying in the 3-photon, where you're really limited in frame rate, where you're starting to have to almost do random access sort of imaging. So you're not sweeping out a complete raster. Instead, you're going to discrete positions and only imaging there. That allows you to both deliver a lot more pulse energy because the average, instead of a million pulses or a million pixels, you're really only trying to take 50. And so you get this big enhancement factor in terms of how much pulse energy you can do within your average power limit. And then the second one is it also becomes a much smaller or much less complex image, and so you can just take more of them. To go back to that first part, off the cuff, it's not obvious how to increase your SNR unless you can look at either the wavelength you're using. If you're already limited out in depth and you really need to go deeper, and so how do you gain some additional SNR? One version would be to try a new fluorophore that allows you to go to a wavelength that penetrates a little bit better, where you can just deliver a little bit more pulse energy at the depth you're interested in. Again, otherwise off the cuff, I think you're kind of locked in to, you got to be able to fill your power budget. Once you're filling your power budget, you start to be limited, and unless you can change color for rep rate.
Great, yeah, those. All right, so can you add time gating to look through the snow? Some of that SNR.
Can you add time gating? So, no, I think is the, boy, So I think what we're asking is if you could, no, the answer is I think no. So the question was, if at the top, if you could basically do time of flight analysis and decide that a photon arrived in a sense too soon versus somewhere a millimeter down. So that difference in space is going to have a very small difference in total time of flight. It's going to be very, very small. Let's even say you could measure it. The second part is that I'm pretty sure without actually doing this calculation, the lifetime of these fluorophores is much longer than the time of flight for the kind of ballistic photon packet to go from the surface down deep. That's going to be orders of magnitude faster than the amount of time that a fluorophore will become excited, it'll go into its upper electronic state, it then sits, right? And that's where we see these exponential decays of population. That exponential decay term is so much longer than the time of flight that I don't think you could ever tease the two out. If I'm wrong, because I'm getting because I haven't turned the crank, I could be wrong, but I think it's the case that no, you would really need something like a spatial pinhole. But then you're adding a spatial pinhole, you're throwing away a ton of light, you're kind of losing one of the key advantages of multiphoton. But I believe I've seen a 2-photon paper where they actually did add a pinhole. So you could do it that way, but you'd almost want to like pop the pinhole in only, it's like you turn the power up as you go deeper, and then at some point you'd even pop a pinhole and then you could keep going. But to even access those depths, recall, you then really need a repetition rate that's really low, well below a megahertz, to actually access these depths that start to look like the fundamental depths.
All right, I think we'll do one more question. How do you change the repetition rate of the Wi-Fi laser without changing much of the pulse energy?
Yeah, so the reason for that on the OPA output having a pretty steady pulse energy is because we run the Wi-Fi in a way that's different than the other kind of microjoule class lasers out in the world. So the Wi-Fi HP is what the standalone 1 micron laser is. We run that for a variety of reasons at a fixed pulse energy. So it's roughly speaking a 3 microjoule laser. And it's 3 microjoules at 1 megahertz and it's 3 microjoules at 4 megahertz, which means that it's 3 watts and 12 watts at 1 and 4 megahertz. And then the nonlinear process is pretty much a pulse energy conversion device. And because we have a fixed pulse energy going in across that repetition rate, we have a fixed pulse energy coming out of the OPA at now 1300 nanometers, where we've shifted out from 1 micron to 1300. But because it's that kind of, it's in a sense linear in the input pulse energy, we maintain that static pulse, or the same pulse energy out. By contrast, most other lasers like the Wi-Fi HP, some of which have more power, they kind of operate in this constant power rather than constant energy. So they have, say, 20 watts and therefore 20 microjoules at 1 megahertz, but there's still 20 watts out at, say, 5 megahertz. And so now they've gone from 20 microjoules down to 4. And therefore, in their nonlinear device, they're going to have this scaling down of pulse energy with rep rate, because it's a conversion in pulse energy that's fixed. And because their pulse energy in is changing so dramatically, it will come out quite dramatically different.
Great. That's unfortunately all the time we have for questions. If we didn't get to your question, also please feel free to email Scott, and he'd be willing to answer some of these questions, or our tech support. I saw some of the questions can be answered by our Thorlabs tech support. And then again, thank you, Scott, for that great presentation. And everyone, please keep an eye out for our next webinars that Thorlabs will be putting on throughout the coming months.